genome look like? Here's its genome. Poly A. And there's different features to it. Okay. The long terminal repeats consist of a repeated sequence, an untranslated region. The 5 denotes that it's to the 5' side, and then a primer binding site. This is the LTR. And then you also have your matrix, nucleocapsid, and your capsid. And then you have your PR, your RT, your integrase. Okay? So, and then you have your surface protein, your transmembrane protein, and then you have another LTR. So you have your repeated polypurine tract, your untranslated region, and your repeat region. So this is what the genome looks like. LTR, stuff in between. Okay, this is the open reading frame for GAG. So your open reading frame GAG encodes the matrix, nucleocapsid, and capsid proteins. This Paul reading frame encodes the protease, reverse transcriptase, integrase gene products. And this one is your envelope, open reading frame. And it encodes the surface and transmembrane. So that's what the genome looks like. So that's the first illustration. So flip back to your notes. All that stuff I said about the genome, you're like, there's just a lot of text. Show me a picture. Here's a picture. So I'm going to continue down here. Early phase. So here's a general scheme of multiplication, or here's the multiplication picture. I'm going to draw that for you guys. So here's the cell. Fix this picture. Okay. Here's a cell. Here's its nucleus. And then you have this. Asshole virus dude. Okay, here's the virus dude. Look at me, I'm a virus. Okay, here's its genome. It's little stupid proteins and everything. It's going to bind to this LDL receptor. And then it's going to undergo fusion. So this is what, step 1? Binding. I should do that in red. Binding. And then you have fusion. Step 2, fusion. This is not step for step. This is just very, very general. It's actually a picture taken out of the textbook. So, well, here it is. There's a little nucleocapsid thing that fully penetrates. Penetration and encoding. So now you just have the nucleocapsid, or a capsid with the thing. And then the 4th step, you reverse transcribe genome. So you end up getting just those 2 lines represent your double-stranded DNA. And you transport, step 5, you transport that double-stranded DNA thing to the cell. And step 6, you integrate. Step 6 is integrate. It's very tiny cell, right? And then, so your end result is you have your viral genes there, and black, you have your chromosome genes on the outside. So this is, I'm trying to show the early stages of multiplication. So, early. That's what that looks like. So you had trouble imagining that. You had trouble imagining, oh, binding and fusion, and what's this whole RT, like reverse transcription stage. This is what it kind of looks like. This is a picture in text, but I literally copied how it looks. So look there. You need to. So 3, 2, 1. Integration. So here's the integration picture. So this is what integration looks like. So you have your viral. This is at this point in time when the virus has already reverse transcribed its genome. Here's its LTR. Here's its LTR. LTR. Actually, I'm going to open up this picture a bit more. Here's the viral genome. Right, remember at the ends of the viral genome are the LTRs. And then you have these tiny sequences way at the end, so even further than the LTRs. SSAG. Textbook. So again, you can always look at the picture in the textbook if you want to. I like it when someone walks me through the picture, so maybe some of you guys like that too. So I'll do my best. Yeah, so here we go. Now, this is a viral genome. And here is a cell genome. Cell DNA is in black, okay? Okay, so here's the cell genome. The thing is, the viral genome will integrate itself at these palindromic sequences. I'll draw that with the arrow. So like on this side, it will insert itself here. I'll use red. It will insert itself there. And on this side, it will insert itself here. And the thing is that it inserts itself 4 to 6 nucleotides apart. So you want to, in this picture, 1, 2, 3, 4. Basically, the end result is integrated viral genome. Okay. So it inserts itself using the enzyme integrase. Okay. So that's how genome integration looks like. We have 2 more pictures. So bear with me. This is a very hard chapter. Remember, this is all in the. This is after the virus has integrated itself, after it's made its this double-stranded DNA, and it's integrated itself. What you want to get transcription, capping, so you have 5' capping, cleaving, and polydenylation. So this picture will help you understand. I will cover this in when you're studying retrovirus. Well, the RNA genome of retrovirus, it doesn't have on the 5' end, it doesn't have this U3. You see it. This is what the in its double-stranded form, this is what the viral genome looks like, but this isn't what its actual RNA genome looks like. And so when it's transcribing its RNA genome, it has to modify this a bit. It modifies this. I'm going to do this side. Blue is the viral RNA. You have the cap here, 5' cap, poly A. You see, when it's going from the double-stranded DNA back to its original genome form when it's transcribing, it cuts out on the 5' side, it cuts out the U3, on the 3' side, it cuts out the U5. It caps it and polydenilates it. And then so this can later on be used to assemble the virus. But when it's making protein, it has to use this. Yeah, splicing. Some of the RNA that's transcribed is spliced. And so let's say, for example, the virus wants to make its envelope proteins. What it would do in order to make the envelope protein, it needs to splice out the GAG-Paul stuff. So I'm not going to write this down, but here's some bullet points I'm going to read off. Making GAG-Paul, the GAG-Paul fusion. So you want to make the GAG proteins and the Paul proteins. You don't need to splice. If you make the enzyme, the envelope ones, the envelope proteins, you need splicing. Now, GAG and Paul come as a fusion because when they are together as a fusion RNA, it allows for proper proportion of GAG proteins to Paul, to polymerase proteins. And the way it does this is that normally when it's being translated, when it's being translated, when it's being translated, the ribosome will read along the GAG-PAW fusion, and it'll make GAG proteins only. So then how do you make the PAW proteins? Well, the way it does that is that 1 out of every 20 times the ribosome will mess up with the stop codon that's in here. With the stop codon, the GAG will be free. And when it messes that up, the ribosome, takes a back step, and then it continues to translate. But when it does that, then you get the polymerase proteins instead. And since it only happens 1 out of 20 times, you are able to make the right proportion of GAG to PAW proteins. And that concept is a concept of ribosome shifting, which I will cover next. Okay, so the concept of ribosome frame shifting. Last picture, and then finally end our processes. So here is the PAW A fusion, or PAW GAG PAW fusion. You have the stem loop structure. There's a stop codon in the stem loop structure. So normally the GAG, and we'll label this as GAG PAW fusion. Normally the ribosome is chugging along, makes everything, and then gets to stop codon and stops. But sometimes same thing, same sequence. AAC, UCC, Here's the thing. Hold on. GAG, PAW, fusion, alternative. Probably should have done this in a different color. But, so color this up. Color that bottom half. But normally you have a normal GAG PAW fusion. Reads everything, yay. You get your GAG proteins. Sometimes, what happens is that the ribosome, it's almost like it's sight reading, like it sees ahead of it that there's a stem loop. It sees a stem loop, it starts to stall. And when the ribosome stalls, it allows for a frame shift. When there's a frame shift, then you shift reading frames and you get the PAW fusion, you get the PAW proteins instead. And the PAW proteins, when they're, it could be the ribosome normally reads and reads and reads. But then when it does the stalling, it might stall here. might read CCA, and it's about to do AAA, but then it sees a stem loop and says, oh wait, let's stall. And then the rhizome stops and it says, wait, we need to start again, we didn't reach a stop codon yet. And it has to usually it backtracks to try and correct itself. It might start here instead. So instead of continuing from here, it backtracks one, and then it starts reading from here. And so you get this shift in frames. And because you shift the frames on one nucleotide, you end up, what should have been a stop codon is no longer stop codon. But these nucleotides now read as the Paul proteins. This is similar to the attenuation that happens in paramyxoviruses. viruses. Yeah, the attenuation. Remember, if you recall, attenuation is when you have one RNA and you're going along, chugging along, and then you hit like a poly U site and you start to stop and stutter, and then that's one protein, and then the rhizome can then start the next set. Maybe a better example is actually, if you recall from paramyxoviruses, you were able, some of the genes that were made is V, P, and C. In a way that it got those three proteins from the same RNA molecule, from the same mRNA, was that for one of them, I think it's like P or something, it's reading is normal, and then suddenly there's a frame shift by one nucleotide, and then you get C instead. So same concept here, but this time there's a stem loop and so forth. It's a bit more complicated. So that is retroviruses. Yeah, it's a lot of information. There's a 2-part lecture, and same thing here. I'm glad to just edit and splice together all these different videos. Hopefully I can get them online by tomorrow, actually Monday. And tomorrow I will then do HIV and herpes virus, and maybe even vaccines, do the video on that. And afterwards I will do basically review videos. The review videos are just me going through essentially redoing all the lecture videos that I give, but as fast as possible. As little text as possible. I might do it here or I might do it at home on my computer. And then, yeah, one last thing, I'm going to post this on Reddit. So, especially if you're a subscriber, or I know I have like 6 subscribers, but sadly they might go away after this class ends. It's going to be kind of sad. It's nice to have 6 subscribers. Anyways, if you're watching this and you want to get together for a review session with me, that'd be great. I don't mind going over this. We should just have a big study party, 10 plus people in the library or something. So, hit me up, or if you see me in class, let me know, say hi, and that's that. I'll see you in the next video. Thanks for watching.